Look, there's not that much here. So to claim you can't do it really is making a pretty big statement to me. I'm pretty sure that we're going to have difficulty down the road. I'm going to set this as the reference level. I think this object is pulled back so that it is above the reference level, a distance of L. The change in height of the object makes me think gravitational potential energy might be something I'll have to use here. Since I see all conservative forces, I think that by the time it makes it down here, it will have converted all of that energy into kinetic energy. There's not a whole lot here. Put those two things together. It starts with an amount of energy equal to mgl, because the height of the bob is a distance L above the reference level. And that's going to be equal to 1/2 mv squared. So v is going to be square root of 2gl. Done this dozens of times. Whether it's a roller coaster, a ramp, or in this case, something on a string. In fact, just be happy. I guess I didn't, do the problem where you pull it up some angle and ask for you guys to figure out how much height it has here. We have a method for this. This should also be in your notes. Something about h is equal to L times 1 minus cosine theta. I can't redo the entire first semester for you, though. You have to bring something to the table. All you who were desperate to get those A's, well, what's the point if you can't remember any of it? But, I don't want to sit here and harp on, disappointment. You can do that all day. So let's get that out of there and do the next part of this that you had difficulty doing, which is that the only way the thing at the bottom can travel in a circular path is if the unbalanced force is equal to MAC. Has to have a centripetal acceleration. And my reminder is that centripetal acceleration is equal to v squared over r. Again, it's all on your equation sheet too. But how to use it? No, it's not on the equation sheet. We know how fast it's going at the bottom. So we know something like this, that's how much the unbalanced force has to be. mv squared over r. R is the length of the string. But on this side, it's got two forces acting on it. Tension upwards, weight downwards. You do the math, and the tension equals 3 mg. The string has to support 3 times the weight of the bob. So, not happy. And not unreasonably so. There's enough different in this new problem. The bottom of the plumb bob traveled at, square root of 2gl. This thing here, well, if we can't remember first semester, I guess I can't imagine remembering 10 minutes ago. That's a long list today. I needed you to be able to do the basics. This is the basics. Because you see that we're extending it a lot. All right? A lot more things to keep track of. They're still going to have to make some concessions. And we've learned enough things where I think we can be successful. But we're going to have to apply all the stuff from first semester and now the stuff we're learning in second semester to be successful. And here's our object. Instead of it being a mass on the end of the string, it is a rod, length L, and mass M. It is held perfectly perpendicular. And then we're going to take that object, release it so that it can swing downwards. Something like so. when it swings down to here, it's moving now. We have to figure out how to deal with this. And it has a lot of similarities. But there are some things that we've talked about earlier in the semester that we're going to have to bring here that you're probably not thinking about. Like, how do we deal with how high this object has been lifted above the reference level? Right? What do we do with that? Now, I've answered this question, but you probably don't know how to apply the answer because I gave it to you a while ago before we had context. In a problem where the object has extension, we treat the center of mass as where the object is. We treat the center of mass as to where the object is. That's huge, but understand that the center of mass becomes a point on the object. And we deal with the object from the standpoint of its center of mass. But you don't necessarily know where the center of mass is to the object unless you're told. There are 3 criteria about how you deal with center of mass. If they tell you that the object is uniform, then the center of mass is at the center. So if the object is uniform, we just treat the center of mass as being a point in the center of the object. They could tell you where the center of mass is. Like I could just say the center of mass is located a distance x away from the pivot point. And they could give you a place on the object. Or, and let's hope this doesn't happen, but it could, they could ask you to come up with the center of mass by using the tools we have from earlier in this semester to deal with center of mass. That's the least likely thing they'll ask you to do. The most likely thing is what we're talking about right now, where it's a uniform object, and therefore the center of mass is at the center of the object. Now, what that means for us is that the reference level for potential energy now becomes where the center of mass goes. I'll say that again. The reference level for potential energy is based on the motion of the center of mass. So when gravitational potential energy is measured as mgh, this h is based on the lowest point the center of mass will go. Again, the reference level is based on the motion of the center of mass. So when we say mgh from now on, h refers to where the center of mass goes. So in this problem, the amount of gravitational potential energy, mg L over 2. This object has less potential energy because its center of mass doesn't change height as much as the object from before. Any question about that? Good. Now, we have another problem. When we allow this object to swing downwards, the way in which it moves is now based on the fact that it's rotating about a fixed point. This object is technically not changing location because it has a fixed point in space. In the other case, where the object was a point mass, we would say it changed location because all the mass was at one end and all of the mass went from one place to another. But a part of this object is staying in place. So we say that this object is rotating. Because of that, our version of kinetic energy has to change. We introduced this yesterday but didn't use it. But for a rotating object, an object that has a fixed pivot point, look, I'm saying these same words over and again. You're just hitting the high points. Don't. Write them all down. A rotating object, an object with a fixed pivot point. This is a certain condition because objects can be rotating and not have a fixed pivot point. This one is an object that has a fixed pivot point. If it has a fixed pivot point, this is the only kind of kinetic energy it will have, rotational kinetic energy. This is because there's a part of the object that's never moving. We treat it like it's fixed in place. You throw a frisbee, it will have rotational kinetic energy and translational kinetic energy. If I take this meter stick and chuck it across the room and spin it at the same time, it would have rotational kinetic energy and translational kinetic energy. But because this object has a fixed pivot point, a point in space that it's attached to, we say it will only have rotational kinetic energy. I've emphasized that a lot. Please make sure that's in your notes because it's going to come up. Now, that means for all of these problems where something's rotating, you have to be aware of what its moment of inertia is. Whether that means that it's one of our basic shapes or something that you have constructed like yesterday, or if you have to shift the moment of inertia, and we'll talk about how to shift the moment of inertia soon. You have to know what the moment of inertia of the system is. For this, it's a rod about its end, so I'm sticking with stuff we already know. Rod about its end is 1/3 ml squared. Again, you have a table, look that one up. So I could ask the question, I think the obvious question, what is the rotational speed of the object when it makes it to the bottom? But I'm not going to ask that question. That one's too easy. It's the same exercise as a moment ago. I want to know how fast is the bottom of the meter stick moving when it makes it to the very straight down portion of its run. Again, I'm asking how fast is the bottom of the meter stick moving? You understand? I'm asking a different question that you're going to have to do something else to get the answer to. Let's see if you can do that. Omega's obvious. You're probably going to have to get that to get to the answer I'm asking for. So if you don't know anywhere to start, we'll get omega. It's the same exact thing you just did a moment ago. Try. You have the potential energy. I want you to set it equal to the kinetic energy at the bottom. It's the exact same thing you've just done, just with slightly different modifications. It's still a whole bunch of letters, I know. More steps, though. Right? More steps. You're going to have to plug in the moment of inertia. Deal with the fact that it's now part. Lots more letters here. I mean, there are things that still have similarities to before, like there's an M here and an M here. Could probably get rid of those. I've got one L here and two L's there. I could probably get rid of one of those. I've got a 2 here and a 2 here. I could probably get rid of those. I mean, there's still algebra to do. But at the end, it looks like omega is going to be equal to the square root of 3g over L. Algebra. There's a lot of it here. And I know, no numbers. You're used to that. This is the second semester now. So we're not going to be holding your hands as much. Of course, this is not the answer I'm looking for. This is how fast the entire thing is rotating at the bottom. It's still a part of what I'm hoping you can do, though. This is a conservation of energy question. The difference is that our object has extension, and because of that, we have to use the rotational rules, not the translational rules. We have used the rotational rules. But we still have this other problem that you guys tend to not fully appreciate or understand, and that is the entire meter stick or the entire rod has this angular speed when it makes it to the bottom. But I asked how fast the bottom of the meter stick is traveling, or how fast the rod is traveling, or the bottom of the rod is traveling, which means you have to do another step. You have to recognize that different parts of the rod are traveling at different speeds. The center of mass of the rod is traveling at one speed. The bottom of the rod is traveling at another. Where on the rod you are determines how fast you're traveling. So at the center of the rod, well, that'd be L over 2 for the radius. For the bottom of the rod, that would just be L. We're still using V equals omega times R, for those of you wondering where it came from, which, if you say it out loud, I'll probably say something mean. Now, just plug it in. This isn't tough. You've got this for the angular speed. You're going to plug it in over here to find out how fast it's going. And yeah, I want you to go all the way with this. And you guys know algebra rules. Follow them. Put that L inside the radical. Get a more comprehensive answer. I want this answer. I want you to compare it to the answer from just a moment ago. The bottom of the meter stick is traveling faster, right? A minute ago when we did, which had all the same dynamics, M, L, those are all the same things. The bottom of the meter stick is traveling faster, and not a small amount, a lot faster. Even though the thing acts on the center of mass, the bottom of the meter stick moves much faster than before. Do the next comparison. I'm just asking you to do the same things. Can you tell me what T is? The tension actually acts here now, at the pivot point. Weight acts at the center of mass. But the problem is still very similar. You should be able to tell me what the tension is. Trying to make some comparisons. It's getting kind of crowded in here, so there we go. I'll make it less crowded. Rewrite the answers for those of you who are still trying to rubberneck to the end there. But I want the tension. Be careful here, please. If it were me and I was looking to do this problem, I'd recognize that we have the rotational speed of the rod, so we could choose to use a different expression for the centripetal acceleration. All right, we have the rotational speed of the rod. Yes, Miga. Again, there's still not a whole lot here. This is still the same problem as before. What's going to be on the left side of this? Nope. I'm sure T will be there, but I don't think it'll be by itself. Is there any other force acting on the rod? The weight should be there too, yeah. I'm thinking T upwards and weight downwards. We just did this question, so it's not. Should be fresh in our mind, right? Now, you have all the things, but what'd you put in for R? I think that's an interesting question, one you should be thinking about. You should be thoughtful about it. It would have to be 1/2 L. This has to refer to where the center of mass is. So when I work this out, we're trying to figure out what force is acting on the object. Yes, the omega is going to be the square root of 3g over L, quantity squared. But R is going to be L over 2. Remember, we treat all the things that deal with the mass of the object as it acts at the point of the center of mass. All right, so, yeah, you can do all that. And here's where I'm not going to do it because you need practice. That's clear. Show that it comes out to be 5/2 mg, please. Show that you can bring something to the table like a little bit of algebra. See, I know that some of you can't do this algebra. M times 3g over L times L over 2. L's cancel. This means this whole thing on the left side is 3/2 mg. I still have T minus mg on the other side. So add mg to both sides and I get mg plus 3/2 mg. Now look, I know some of you struggle with algebra. I know it. One of the reasons you struggle is you refuse to write out enough steps, but you also refuse to see things that can be combined together. This is 1 mg plus 3/2 mg. If it bothers you, factor out the mg. Now it's just 1 plus 3/2. If you don't like that, then it's 1 plus 1.5 or 1.5. I'm just not scared of fractions. So I leave it in fractions. You don't have to. If you're desperate, make it 2.5 mg. Just numbers. I just tend to deal with fractions. I think they're easier. Understand, there's a lot here. I needed stuff I haven't asked about yet, but I'm gonna wait. I'm gonna focus just on energy for today. So let's find a new way for you guys to prove how awesome you are. How about a So I have a box on the top of a ramp. Let's say the ramp is H high and L long, and the box has mass M. And for the time being, let's say that there is no friction between the box and the surface. I release the box at the top of the ramp. How fast is it going when it's traveled the distance L? But I'd argue we just did this problem twice already. Does the object have a clear change in height?
Yes.
Is there any friction involved in the problem? So I'd argue that whatever energy it has at the top, same amount of energy at the bottom. I'm thinking it's got mgh at the top. At the bottom, does it have any gravitational potential? No, it's at the bottom. It's at the reference level. So at the bottom, all that energy is now kinetic. Look, the fact that you guys had to second guess this, you can see why it bothers me a little bit, right? So you know where I'm going to go with this, right? You do understand what's going to be next? I mean, I hope that you do. Because probably the next thing I'm going to do is to take away the fact that this is a block. Oh, wait, we need those things. We don't need that. There, get everything back where it goes. And let's replace it with, I don't know, something round. There we go, something round. And before you run along and start doing this, would you agree that this is a similar question? Now, be careful. The answer for how fast this is going when it reaches the bottom is still this. If there's no friction, would the object roll down or slide down? For situations in which an object is going to have the possibility to roll, you need to check first whether there's actually something to make it roll. This is new information. A lot of this stuff is new today. But if you jump to the idea that this will just roll down to the bottom, don't. Things roll because of purpose. Something causes them to roll. An unbalanced torque spins the object. What do you think would cause the object to spin? Friction's a good possibility. If there's no friction, is there any reason for this object to spin? No, this will just slide to the bottom. even when I start to say, okay, so there's some friction on the ramp, that's not necessarily enough to say that it's going to roll. There are three possible outcomes to a problem like this. There's pure sliding. That means omega equals 0. Or the change in omega equals 0. I'm saying both of those because both of those are possible. This is a situation in which the friction equals 0. There's no change in the rotation of the object if there's no friction. The next condition is called slipping. Slipping means there's enough friction to cause a change in rotation. Do I have to say that 10 times, or is that one time good enough for you to get it down? Slipping means there's enough friction to cause a change in rotation. Doesn't mean it's rolling. The third condition is rolling. Rolling is a specific condition and has a specific meaning. Rolling exists when this is true. That is the condition required for there to be rolling. A link between the linear motion and the angular motion. There has to be enough friction, long enough to spin the object up so that it rolls. So these are all possibilities. You need to evaluate. If they say the word rolling, you're fine. This is true, and the object rolls down the ramp. If they don't say the word rolling, you better pay closer attention. So look for the word rolling. It is a signal. They're saying something. Now, I'm seeing the beginnings of people checking their phones and packing up. I love that. That really makes me feel great about myself. I'd argue that you should be really good at this then by tomorrow, because you're telling me that I don't have to worry too much. But I think you should tell me how fast something is rolling down this ramp. Let's say that this is a disk and has a moment of inertia of 1/2 mr squared. And I say that the condition is met for it to be rolling when it makes it to the bottom of the ramp. There's new material here, and we've never done this before. But the object still has the same amount of gravitational potential energy. That hasn't changed. We did this, right? We put the little things on the table and rolled it down the table. So when it makes it to the bottom, it will have two forms of kinetic energy. They'll be translational and rotational. Now look, I don't want to be disappointed tomorrow. Can you try this tonight? I'm not asking much. I'm asking for you to use this and this and this. Try putting them all together. You will notice something, I hope.